Number 1, explain why there may be an infinite number of values for the reaction quotient of a reaction at a given temperature, but there can only be one value for the equilibrium constant at that temperature. As the equilibrium is establishing, those concentrations are changing, so the reaction quotient will change with the changing concentrations. One of the defining points of an equilibrium is where there's a steady state in those concentrations, so they effectively don't change. And that's why there is one value for the equilibrium constant, but there can be an infinite number of values for the reaction quotient. Number 2, explain why an equilibrium between bromine liquid and bromine gas would not be established if the container were not a closed vessel. Well, that's because the gas would then be escaping to the room. It's not a closed system. So that bromine liquid would be evaporating into the gas, or more of the liquid would be evaporating into the gas than the gas recondensing into the liquid, because that gas would then be escaping. Number 3, if you would observe the following reaction at equilibrium, is it possible to tell whether the reaction started with pure NO2 or with pure N2O4? Well, if it's at equilibrium, it will be impossible to tell. Because at equilibrium, you will form a steady state. It doesn't matter what you started with at equilibrium, it will look the same. Number 4, among the solubility rules previously discussed, write the expression for the equilibrium constant for the reaction represented by this equation. Well, because we would be the concentration of the products raised to their appropriate coefficients divided by the concentration of the reactants. But we do not use solids in our equilibrium constant expression. Therefore, this value would be greater than 0, but we would assume it would be less than 1 because silver chloride is insoluble. Remember from Chem 1 that means that very few of these particles would actually separate from the solids. Number 2, write the expression for the equilibrium constant for this reaction. Lead chloride is also insoluble. And here, again, the solid does not enter into the equilibrium constant. So we would use a 1 for the numerator, and then the concentration of the lead ion times the concentration of the chloride raised to the second power, or squared. This value is also going to be less than 1 because, as we have set it up, it is a fraction. Lead chloride is insoluble, so as these ions are out of solution. Number 5, we're going to take approximately the same approach, but this time we're going to be looking at carbonates and phosphates. So if carbonates are insoluble, so this is an insoluble compound, and we need to write the equilibrium constant reaction, then it would be the concentration of the calcium times the concentration of the carbonate, and there's a typo there, that should be a 2 minus. And that would be expected to be less than 1, and that's because calcium carbonate is insoluble. So if you drop calcium carbonate into water, you can expect that very few of these ions would be produced. Number 2, write the equilibrium constant expression for this compound. Again, barium phosphate is insoluble. So as these ions are floating around, this barium phosphate would drop out of solution. Now we would use a 1 in the numerator. We do not put the concentration of a solid into our equilibrium expression. And then that would be over the concentration of the barium cubed times the concentration of the phosphate squared. Now this is set up as a fraction, so we can expect this to be less than 1. Number 6, we have these compounds, benzene and acetylene. So we convert acetylene into benzene. Which value of Kc would make this reaction most useful commercially? Well, if the Kc was 10, so much more product create equilibrium, then this would be a very useful reaction commercially. Number 8, for a titration, which is a lab technique, for a titration to be effective, the reaction must be rapid and the yield of the reaction must essentially be 100%. So would the Kc be greater than 1, less than 1, or approximately equal to 1 for a titration reaction? Well, the Kc would be greater than 1 because we need more products than reactants.